All right, so we're going to look at a particular base that's going to be very useful for us. Um, and this is the natural base, which is denoted by the letter E. And E is defined as 1 plus 1 over n to the power of n, but we're going to push n all the way out to infinity. And this it came about from calculating interest, but the idea is if I'm multiplying something by e, I have itself plus some fractional component, but that fractional component gets smaller, and then I multiply it, it gets compounded. So that's what the idea is. Let's look at this number. So what I've done here is I've set up a spreadsheet. And what I've done in this spreadsheet is I've put n values, and I've done up to 10 and then up to 90 and up to 100. And what I did over here is I put the formula 1 plus, let me get my division here right, 1 divided by n to the power of n. And so what I'm going to do is I'm going to calculate that as n gets bigger. So I do that by dragging it down here. And I'm going to get the first 1,000 values. Well, up to n being 1,000. Now what happens is notice the number starts at 2 and it gets bigger. But it gets bigger more slowly. And let me keep making n bigger. This is what mathematicians did to find this value. And there's some neat calculus that ends up getting done. And this actually has a value, kind of like pi. We can't write it as a fraction, but it can keep, but it is an exact number. That's the problem with us writing. Let's see here. 6,000. So I'll take it up to 6,000. We'll try to see if I can get my computer to top out here. So I no longer I got up to 2.5, 2.6, 2.7, and now I'm not seeing much motion in this number. So let's make these numbers bigger. 50,000, and then maybe 100,000, and 500,000. And we'll just keep calculating our values of E. And it's slowly approaching a number. Notice how my change was in the first decimal place for a while, and then it was in the second decimal place for a while, third, and now we're changing all the way over here. And so E is a number that has a value approximately, let me get over here, and let me switch over for you here. I switched over for me. There we go. The approximate value of E is 2.718. Let me get my 81287. 2.718. I'll actually get my calculator and verify that. I never trust my own handwriting. And most calculators should have a key for E. It's usually around your natural log key. And we'll talk, those two things go hand in hand. It's 2.718. 2.71828 and the next number on the calculator is 8, but there's some rounding going on here. And this number repeats forever, just like pi. E is probably the most important base in mathematics. The E will pop up in every chapter we do here in some form or another. And it has some important properties, and it's really about this definition here of how it is a whole plus an ever decreasing part. And that makes it do a lot of important things in calculus. And E gets used for a lot of things. But it's a base that we'll be using where we'll say E to some power. And this is a preferred form. For example, I can talk about population growth as it's doubling time, and I can talk about how much it doubles with time. Right? This is how quickly it doubles, and time is my variable. But this part here, 2k, I can write as e to something. And because e is common and natural, a lot of disciplines will use e as their base instead of this number. And we'll see when we work on the inverse, the logarithm, there are only a few calculator keys for logarithms, and e is one of them. So just be aware we can write the same thing, 2 to some power times t, as e to some power times t. And we can make these two things equal. And we'll find as we do some data models, your calculator will spit out some weird bases sometimes. And it's better to put the weirdness into this than the base. But E is the natural base, and it pops up. And we're going to see that in the examples we're going to do now. So what we're going to do is we're going to look at interest on borrowing money and population models. So let's look at a population model, and then we'll look at a compound interest model. So in population models, we can get the idea that I have some population, I'll make P, as time goes on, that population grows. So I'll have some initial population. And what we tend to do is we put P0 down at the bottom. We're saying the population at time 0. And then we'll take it to E as time progresses. So this is very similar to our f of x equals b of x, but we're going to have something out front which shifts it, so that's the original value. And instead of x, we're going to talk in time. And our base is specifically going to be e. And now we're going to want to shift time. Some populations grow fast, some grow slow. So we put, I'll use a Greek lambda here. Sometimes we'll use k. And that's the rate, the growth rate. And this is how we can model populations growing, money growing, any set of systems where the growth is determined by how many things are in it. They grow exponentially. And so, for example, I can talk about a population model where, let me get my numbers from the book here. We have 1,144 species to begin with. So 1,144 is P0. That's how many are initially there. We're going to take it to E, and it has a growth rate of 0.325. So for my model, I'm saying lambda is 0.325. And time will go on. So when time is 0, t is 0. So anything times 0 is 0, and anything to the power of 0 is 1. And so our initial population. And so this is why this thing hanging out front is called the initial population. Well, after a set amount of time, And let's see what I want to look at here time-wise. Let's figure out what happens um, in 35 years. So we'll say P0, 35 years later. So we want P when 35 years have passed. So I take my initial model here, and I get e to the 0.325 times 35. And again, I'm going to jump on my calculator here. I always double check my work. And let's see, so I'm going to have 1,144 times e, which is on my calculator by the ln key. And that's going to be 0.325 times 35 in the exponent. And that says that this, sure, I'm close on that. Let's see. 35, 0.325. Oh, let me fix my percentage here. I want 0.325 is a 32% growth rate. Oh, let's put that in. This would give me a value of 1,144. 0.325 over 35 years gives me 1, 2, 3. Right? It's a very fast growth rate. That's a 32.5% growth rate. And that's a high growth rate. I think the problem I wanted to do is let's see what happens if the growth rate slows down. So let's look at a slow growth rate on a different population. So let's say we start with a different species. Let's say not like a bacteria. It begins with a population of 755, like wolves in captivity. E2, and it's going to have a growth rate that's 0.05 T. And so here, my initial population is 755. My growth rate is 0.05, which that means 0.5% compared to 32% up there. And so let's see what happens after 35 years of this growth. And so I go back to my calculator, and notice calculators are going to be tools that you need to work on these types of functions. They are not easy to calculate by hand. Help if I'd put a decimal place in there. Let's do that. And this gives me 899.39. Of course, you can't have half a 0.3 of an animal, so we'd probably round down. And so this is how population models work. E was also used in interest. And in the next video, we'll look at interest without E and interest with E as our examples.